Hey friends, welcome to my channel. In this video I am going to discuss about 5 important terms which are very important in terms of organic chemistry, because whenever you read a reaction in one of these terms will come, and that are namely the selectivity terms: the chemoselectivity, regioselectivity, stereoselectivity, enantioselectivity and diastereoselectivity. And in this regard I will also talk about the difference between stereoselectivity and stereospecificity. So first term is the chemoselectivity. So these three terms, chemoselectivity, regioselectivity and stereoselectivity, they all are some kind of selectivity whenever you are doing a reaction, but the way of the selectivity or the type of the selectivity is different, and you have to ask these three questions to get what kind of selectivity it is. Now whenever you are talking about chemoselectivity, you have to ask your molecule that whenever you are taking a molecule, which group will react. So if you have one group, that is fine, but if you have more than one group, then the question you have to ask is which group will react. For example, let's say you have this molecule para-aminophenol. So in this molecule there are two groups, one is amine group and one is the hydroxyl group, and both groups can react at more or less same condition. For example, when you do acetylation, if you put acetic anhydride in excess, you will get acetylation at both O and N, and you will get this compound OAC and NHSE. Sorry, NH not AC, this is NHOMe. Okay, so this compound you will get if you add acetic anhydride in excess. But by varying the acidity or basicity of the medium, that means the pH of the medium, you can get either N acetylation or O acetylation, and this is the question of the chemoselectivity, that between these two groups which will react. In this case, if you do the reaction in one equivalent acidic anhydride and basic medium, then N acetylation will occur, because at that time the NH2 group will be more reactive. On the other hand, if you do the reaction in acidic medium, then NH2 group will be protonated as NH3 plus, and then only the OH group will react. So accordingly you will get your desired product. Now the same kind of selectivity question comes. Let's say in your molecule you have a ester group and one aldehyde group, and you want to reduce this compound. Now if you consider the electron deficiency of the ester and the aldehyde will be more electron deficient, and that's why when you do reduction you can exclusively reduce either of these two groups by varying reaction condition. So this is the question of the chemoselectivity. Then after that, the term which comes is the regioselectivity. So regioselectivity, the name itself implies that it deals with the region or the reaction center of a particular molecule. So in this case, let's say you have only one functional group in your molecule, but the centers which can undergo the reaction is different. For example, let's say you have a alpha beta unsaturated compound like this. So in this case you can see this is a total one functional group alpha beta unsaturated compound, but when you do a nucleophilic substitution reaction here, the nucleophile can either attack this 4 position or it can attack this 1 position. So whether it will do attack at 1 or 4 position, that is the question of the regioselectivity. So in this case you have to ask the question where the molecule will react. So now we know that if soft nucleophile you use, it will react at 4, and if you use hard nucleophile it will react at 1. The similar regioselectivity question comes for a electrophilic or nucleophilic substitution reaction in an aromatic compound. Let's say here you have any group R. So whenever you are doing a electrophilic aromatic or nucleophilic aromatic substitution, you have a choice between ortho and para position. So this is the case of regioselectivity. And finally the third selectivity comes, and it is the stereoselectivity. Now stereoselectivity means how the molecule will react, that is the mode of reaction. So in this case you can get one stereoisomer over another, and stereoselectivity is classified into further two terms, and that are the enantioselectivity and the diastereoselectivity. Enantioselectivity implies that in a particular reaction, if you have the possibility of getting two enantiomers, but you are getting one particular enantiomer in major and another one is minor, so then the reaction is called enantioselective reaction. Whereas in case of diastereoselectivity, if you get if there is a possibility of getting two diastereomers, out of which one you are getting as major, then it is called the diastereoselectivity, but both are the stereoselectivity. Now there is another term called stereospecificity, and many times people have a misconception that more stereoselectivity means it is stereospecific, or 100% stereoselectivity means it is stereospecific, but it is absolutely wrong. The two terms are totally different. Stereoselectivity means whenever you have a choice, that is, in this case, you what starting material you are starting with, that doesn't matter. In this case, you have a pathway, a favorable pathway which the molecule choose to give you a particular product. For example, let's say you are doing a elimination reaction like this. You have this compound, so here you have pH, OH, and this CH3 CH2 CH3 group, and you are doing elimination reaction in concentrated sulfuric acid. Okay, so now this center can have two isomer, either it can be R or it can be S. So it is actually shown like this. So either it can be R or it can be S. But if you do a E1 elimination reaction in this case, that is by the formation of a carbocation here, then every time you will get trans product as your major product. So this trans alkene you will get major. So in this case, you are stereoselectively getting the trans product. So this is a stereoselective reaction. In this case, whatever starting material you are using, that doesn't matter. Your product will be always the one which goes through the favorable pathway or the lower energy demanding pathway. So this is the case of stereoselectivity. Now for the case of stereospecificity, what is stereospecificity? Let's say you have this compound. So in this case, let's say you have a OH group here, and sorry, not OH group is not needed. Let's say you have a normal cyclohexene or any normal alkene, and now, so let's say more good example. So let's say you have a cis alkene like this, and you have another trans alkene like this, and you are reacting both of this compound in separate reaction medium, and you are reacting them with, let's say, metachloroparbenzoic acid, same metachloroparbenzoic acid. So in this case, for trans case, you will get a epoxide which will have the trans configuration, whereas for the cis isomer, similarly you will have a cis isomer. Okay, so in this case, the stereochemistry of the starting material will decide what will be the stereochemistry of the product. You can never get a trans epoxide starting from a cis epoxide. Whether the cis is more stable or less stable, that doesn't matter. The thing which matters is the stereochemistry of the starting material. Similarly, if you do the dihydroxylation with osmium tetroxide, let's say with osmium tetroxide you are doing dihydroxylation, so in this case you will get a cis product, whereas in this case you will be getting a trans product. So these two reactions are the examples of stereospecific reaction. They are totally dependent on the stereochemistry of the starting material. So this is called a stereospecific reaction. So this is the main difference between stereoselectivity and stereospecificity, that for stereospecific reaction, the outcome of the reaction is totally dependent on the stereochemistry of the starting material and also the reaction condition, but the stereochemistry of the starting material is more important, and in this case the favorable pathway doesn't matter. What is the favorable pathway? Always you will get the pre-decided product, whereas for the stereoselective reaction, the reaction will always goes through the more favorable pathway or less energy demanding pathway, and accordingly you will get one major and one minor. So for stereospecific case, you will get only one product, no major, minor. Now the enantioselectivity and diastereoselectivity. So actually diastereoselectivity means whenever you are doing a reaction and you are getting one diastereomer as your major product, so this is called diastereoselectivity. For example, the same epoxidation reaction, let's say you are doing epoxidation reaction with this particular compound. So if you do this reaction with metachloroparbenzoic acid, in this case you know that chelation will occur and you will get this as major product, where your epoxide will form on the same side where the OH group is, and this will be your major product. Okay, this is your major product, and this will be your minor product. Actually, this amount of this product will be very less, almost exclusively you will get this product, but again there is a major minor. So this is called diastereoselective reaction. These two are diastereomers, and you are getting this diastereomer as a major over this. Similar example we can discuss, like let's say you have this cyclohexanone, this one, and you are doing this reaction with, let's say, sodium borohydride. So sodium borohydride is a small hydrogenating agent or small reducing agent. So in this case the stability of the product is more important, and in the product the OH group is bulkier than the hydrogen group. So in the product you will get the OH group in the equatorial position and the hydrogen in the axial position, whereas if you do the same reaction with, let's say, chemoselectivity, then you will get the different product. That is, here you will have the OH this side and hydrogen this side, because in this case the size of the attacking reducing agent is bulkier, and that's why it will prefer to attack from the less sterically demanding side, that is from the equatorial position, and you will get this product. So you can see these two products are two diastereomers. They are not enantiomers, but they are diastereomers, and so this is a diastereoselective reaction. Now there is no true enantioselective reaction because you can see for a enantioselective reaction the precursor for the precursor the two phases of attack should be enantiotopic. For example, let's say you have an alkene, so these two phases of this alkene are so let's say here, yes, so two phases of this alkene are enantiotopic. Or let's say you have an carbonyl compound like this. Here you have RL group and here you have RS group. So in this case also, if there is no stereo center or no chirality between this RL and RS, if they are only simple alkyl groups, then you can see the plane. The plane is not a chiral plane, but it is a the two phases of the plane will be enantiotopic. So in this case there is no favorable phase. The both phase can be attracted with equal is 50-50%. So there is no actually there is no enantioselectivity. But if you remember the Sharpless epoxidation reaction, what happens for Sharpless epoxidation is that this is your compound for Sharpless epoxidation, and when you do this reaction with, let's say, with L-date, you will get a epoxide which will form above the plane, whereas if you use plus date, so this is D date, this is L date, or this is minus date, this is plus date. Date means diethyl tartarate. So in this case you will get the epoxidation as in the lower phase. Okay, so you can see the starting material here is also not chiral, and its two phases are enantiotopic phases, but still it is giving two products in two different conditions. And this is the case of enantioselectivity, because these two isomers are the enantiomer of one another. They are not diastereomer, but they are enantiomer. So actually overall it is looking that you are getting one enantiomer over another, but in the reaction condition what happens due to the chelation with the catalyst use, the two phases they then remain no longer they are enantiotopic, but they become diastereotopic, and in situ you are making the two phases diastereotopic, and that's why you are getting one enantiomer over another enantiomer. So at first they will form as diastereomer, not enantiomer, but after workup you will get two enantiomers. So overall the reaction is an enantioselective reaction, but the actual mechanism is a diastereoselectivity. So this is the case, and for this particular reaction you can see I already told that with the metachloroperbenzoic acid depoxidation reaction is a stereospecific reaction. So this particular example is at the same time it is stereoselective and stereospecific. So stereospecific in the sense that the epoxidation will always lead to the cis product, because your starting material is cis. So you can see this alkene is a cis alkene, so starting material is a cis alkene, so you will always get a cis epoxide. But the stereoselectivity means you will always get the epoxide which has the oxygen atom on the same phase where the OH group is. So this is the case of stereoselectivity. So this is an example of both stereospecificity and stereoselectivity. So I hope with all these examples you are able to understand what are this term mean, and I'm able to clear your doubts about this particular selectivity terms. So if you like the video, then give thumbs up and share this video with your friends, and also if you're new in this channel, then subscribe my channel, and thank you for watching.